We've used all of these rules, but now we'll actually formally discuss them. In Chapter R, we saw that there was a difference between an expression and an equation. Again, the important thing to remember is that an equation has the all-important equal sign. You solve equations, which means you find the value of the variable that makes the equation true. Expressions, on the other hand, do not have an equal sign, and all you can do to an expression is simplify or evaluate. Linear equations in one variable, ax plus b equal to c, that's how they're written. An equation is linear if the degree is 1, which means the highest power appearing on the variable I don't know what I'm doing that makes that happen, is a 1. To solve a linear equation means to find the value of the variable that makes the equation true. Now again, we've used all these properties, but now we'll actually define them and show you how to properly use them. Any equation is a scale balance. It'll remain equal as long as you balance the left side with the right side. You can perform any mathematical operation as long as you perform that same operation on both sides of the equal side to maintain the proper balance. The first rule is the addition sign of equality. If a equals b, and if c is any real number, then a plus c is equal to b plus c. In example 1 here, in this first part of the example, this is not the typical way someone would use this, but it's still true. If you started off knowing that x is equal to 5, you can add 2 to both sides. X plus 2 equals 5 plus 2. You still get a valid, true statement. Now, it's more useful, however, if you had an equation like x minus 2 is equal to 3. You would deal with this equation by adding 2 to both sides. It still leaves the equation unchanged. The solution to the equation is unchanged as long as you do the same thing to both sides. The 2's cancel, leaving just x on the left-hand side, and 3 plus 2 is 5. So the solution there is x is equal to 5. Moving on to more of these properties. The second property is the subtraction property of equality. Again, it's the exact same idea. If x plus 2 is equal to 7, then to get x by itself, to get x completely by itself, we would simply subtract 2 on both sides of this equation. The 2's would cancel. The 2's would cancel, leaving x is equal to positive 5 as the solution. The next rule is the multiplication property of equality. Now for this one, let me ask, 1/4 times x is equal to 8. What do you think you would like to multiply by so that you can get x alone on the left? Well, since we already talked about reciprocals and multiplicative inverses, I'm hoping it occurs to you that we should multiply both sides by 4, because 4 times the reciprocal 1/4 will leave a 1. Then you'll get 1x, which is x by itself. So let's multiply both sides here by 4. 4 times 1/4 x is equal to 4 times 8. Again, 4 times 1/4, you just get left with a bunch of, I don't know why that keeps happening, a bunch of 1's. You end up with 1x, which just means the same thing as x. And 4 times 8 is 32, so the value of x would be 32 to make this equation true. Note, this property is only valid if c, the thing you're multiplying by, is not 0. That would change the value of the equation. The same thing here for the division property of equality. You can divide by anything, which is what c is, as long as the c is not 0. So for example, if you have that 3x equals 18, you want to get x by itself. Simply divide both sides by 3. The 3's cancel, leaving a 1, and you would get that x is equal to 6. Note, the important thing to remember is that when you solve an equation, The idea is that you are trying to get all the variables on one side and all the numbers on the other. It doesn't matter if the variable is on the left or on the right side of the equation. So here are some rules about how to use all of these rules together. Step 1, always simplify the expression, both sides of the equal bar. What I mean by that is to distribute and remove any parentheses in the problem. Another thing to be aware of, if you have a coefficient that is a fraction, multiply by the least common multiple of all of your denominators to clear the fractions. We already did an example that involves this, but we'll do another. The second thing to do is add or subtract any constants, and then to remove them from one side of the equation, remember to perform the operation on both sides. You can also do your variables first, so either move all the variables or all the constants. That's step 3. Add or subtract any variables so they are on the other side of the equation from the constants. Again, remember that whatever you do to the left, you must also do to the right. Then multiply or divide both sides of the equation by a constant that makes the coefficient on the variable a 1. Once you make it to 1x is equal to a number, you have your solution. Now, we did examples 1, 2, 3, and 4 at the very beginning, so why not move on to examples we have not already done? So moving on to page 5's examples, again, these are already done at the beginning. Maybe you can try them yourself and check the beginning to make sure you got them right. Some more examples that we haven't done. -5 times the quantity 3w minus 3 plus 1 plus 16w is equal to 0. The first thing you need to make sure you do is distribute anything through and remove any parentheses that can be removed. So the -5 gets distributed. This will give us -15. I don't know what just happened. I'm a page behind. -15w. And -5 times -3 makes +15. These parentheses right here are not really doing anything. They're separating addition from addition. So let's just drop them because they aren't really doing anything. And then we'll be able to combine like terms. The -15 and the +16w make 1w. The 15 plus the 1 here make +16. Subtract 16 on both sides, and you get the w is -16. -5p plus 4 equals 19. Again, the goal here is to get the p completely alone. So subtract 4 on both sides. And to get p completely alone, divide everything by -5. 15 divided by -5 is -3. 2q plus 3 equals 4q minus 9. So again, we want to get all the q's on one side and all the constants on the other. So this 4q needs to be moved over here, and this 3 needs to be moved over there. So why not do this all in one fell swoop? So 2q plus 3 equals 4q minus 9. So what I mean by that is I want to move all the q's over to the left. So I'll subtract 4q on both sides. But why not simultaneously move the 3 over to the other side? So subtract 3 on both sides to get rid of that. So then, combining like terms now, you're adding these guys together. 2q minus 4q is -2q. The +3 and the -3 make a 0. You don't typically write that, you just leave it off because it's not contributing anything. It's just gone now. The 4q and the -4q make 0. -9 minus 3 is -12. -2q is -12. Dividing everything by -2, we get the q is +6. Looking at this next example, 7 times the quantity p minus 2 plus p is equal to 2p plus 4. Again, the first thing you want is everything to be opened up so you can combine like terms. So the first thing that needs to happen here is the 7 needs to get distributed through. This will give 7p minus 14 plus p is equal to 2p plus 4. On the left, you can combine 7p plus p, 8p minus 14 equals 2p plus 4. Again, now from here, why not just do this all at one time? Move the 2p over, move the 14 over. To do that, we'd have to subtract 2p on both sides, and then add 14 to both sides to move the 14 over. 8p minus 2p is 6p. Negative 14 plus 14 makes 0. We don't write it. 2p minus 2p makes 0. We don't write that. 4 plus, I lost a 1. 14 equals 18. To get p completely alone, we divide both sides by 6 and get that p is equal to 3. We have 2 more questions to go, but I think we need to stop the video here so it is allowed.